look up on a clear night, and the universe seems populated by millions of identical, peaceful white dots. But that uniformity is an optical illusion. The cosmos is actually a wildly diverse zoo, filled with stellar objects of incredibly different temperatures, sizes, and temperaments. Our own star, the Sun, is just one specific breed among many. It belongs to a middle-aged category called yellow dwarfs, and as you can see up close, it is a turbulent sphere of fusing plasma, constantly racked by violent magnetic storms. Curious, if our Sun represents just an average, middle-of-the-road star, what kinds of monsters and dwarfs make up the rest of the galaxy? And exactly how do all these different stars end their lives? To answer that, you only need to know one rule of astrophysics. A star's entire destiny is dictated by its birth weight. The amount of mass a star gathers when it forms determines every stage of its existence, right down to the violence of its death. It is a strict inverse relationship. The lighter a star is, the longer it will live. The heavier it is, the faster it burns through its fuel, guaranteeing a rapid, catastrophic demise. Understanding this single rule allows us to map the lifespan of everything in the night sky. At the absolute bottom of this cosmic weight class are brown dwarfs. These objects gathered some mass, but never enough to trigger continuous hydrogen fusion in their cores. They act like failed stars, trapped between heavy gas giants and true stars, slowly cooling and dimming in the dark. Step up slightly in mass to find the most common objects in the universe, red dwarfs. They make up roughly 75% of all stars. Because they are so small, they sip their hydrogen fuel incredibly efficiently. This means a single red dwarf can burn steadily for over 1 trillion years. The universe itself is only 13.8 billion years old, meaning no red dwarf in existence has even come close to dying yet. Next are orange dwarfs, sitting right between those tiny red stars and our Sun. They carry a bit more mass, warming them to around 4,000 Kelvin, and they shine steadily for 15 to 30 billion years. Because they lack the violent solar flares common in red dwarfs, astrophysicists consider them the most stable environments in the galaxy, making them prime candidates to host habitable, life-bearing planets. If your goal as a stellar object is longevity, being small, cool, and dim is the ultimate survival strategy. Our Sun sits further up the mass scale. At this weight, fuel is consumed much faster, capping its total lifespan at a modest 10 billion years. Our star is currently exactly halfway through that cycle. This animation projects what will happen in roughly 5 billion years when the Sun's core finally exhausts its hydrogen. It will begin fusing hydrogen in a shell around the core, forcing its outer layers to swell outward into a red giant. As it expands, it will completely swallow the orbits of Mercury, Venus, and almost certainly Earth. After this swollen phase, medium-mass stars do not explode. The star will gently shed its outer layers into space, leaving behind an extraordinarily dense, Earth-sized core called a white dwarf. The star simply puffs away its atmosphere and leaves a heavy, glowing ember. With no new fusion occurring, that white dwarf will spend the next several billion years silently radiating its leftover heat until it goes entirely dark. Move to the top of the mass spectrum, and the physics become extreme. Massive, blazing hot blue giants and unstable Wolf-Rayet stars have surface temperatures exceeding 30,000 Kelvin. They burn through their immense fuel reserves at a furious pace, living for only a few million years. This diagram shows the sheer scale of a red supergiant like Betelgeuse. If you look at the comparison key at the bottom, if Betelgeuse were placed at the center of our solar system, its surface would extend past Mars and nearly reach Jupiter. Carrying that much mass has a fatal consequence. When a titan like this runs out of fuel, the outward pressure of fusion stops, and gravity instantly crushes the star inward. The core collapses in seconds, and the resulting shockwave violently rebounds outward in a blinding supernova explosion. What remains after that detonation defies common sense. A collapsing core between 1.4 and 2.1 solar masses compresses into a sphere just 20 kilometers across, creating a neutron star. The density is so extreme that a single teaspoon of this material would weigh 6 billion tons on Earth. Many neutron stars rotate hundreds of times a second, emitting focused beams of radiation from their magnetic poles, like cosmic lighthouses. When the beam sweeps past Earth, we detect perfectly regular radio pulses. As you can see in this photograph of Jocelyn Bell Burnell, who discovered them in 1967, the signal was so perfect that researchers initially considered the possibility it was an artificial broadcast from an alien civilization. An even more extreme variant is the magnetar. These rare neutron stars generate magnetic fields up to 1,000,000,000 times stronger than Earth's. If a magnetar were positioned halfway between here and the Moon, its magnetic field alone would wipe the data from every credit card and hard drive on our planet. But if the collapsing core is heavier than roughly 20 solar masses, gravity wins an absolute victory. The collapse never stops. As seen in this 2019 photograph of the supermassive black hole in galaxy M87, the remnant crushes down to a point where gravity becomes so intense that not even light can escape the event horizon. Immense mass grants a star unparalleled luminous power, but it guarantees an agonizingly brief existence and a monstrous, inescapable afterlife. Every category we've explored reveals the same struggle. A star is an active nuclear furnace, locked in a constant, desperate war against its own gravity, and that war is the reason we exist. When the most massive stars lose their battle with gravity, the immense heat and pressure of their final supernova explosions forge all the heavy elements required to build solid rocky planets and biological human bodies. If the universe were perfectly safe, if it only contained long-lived, well-behaved stars like red dwarfs and our own sun, there would be no calcium, no iron, and no carbon scattered into space. The cosmos would be entirely sterile. A violent death of a massive star is not a tragedy. It is the engine of creation. We are quite literally the byproduct of stellar mass, forged in the ashes of giants.